What?
All right. So, like I told Ed, we're going to talk about all the effects of the sun.
And nothing about the daughter.
Right. So we'll talk about sunspots and solar radiation and some ionospheric disturbances, some special propagation modes that you may or may not ever encounter. I don't think we have a chance of doing the
Aurora.
equatorial or the aurora or the equatorial, although the aurora got close here a while back.
Yes,
it was
it
in
did.
Georgia.
I know.
But the trans-equatorial one, you got to be about 2,000 miles north and south of the equator. So I don't think we can make that.
No, short.
In fact, doesn't that almost make it Canada? 2,000 to 3,000 miles north of the equator.
Probably.
Meteor scatter, a little more about Earth, Moon, Earth, or moon bounce. Some of the propagation techniques that they use and the indices, which is probably the hardest part of this to remember, what the A and the K and the G do. And a little on circular polarization at the end, which is a special case of elliptical. How do I get up there? What's going on here?
Got a URL on your page. Next slide.
The mouse is really messing up. Okay, so the sunspot cycle is the thing that has the most effect on HF, and it's the 11-year cycle. We're about to peak. It's cycle 25 from when they started counting cycles. It's obviously more than that. They use the thing called the sunspot number to indicate the number of sunspots, anywhere from 0 to up in the 200, 250 range. It's usually the higher the number, the better the propagation, because it means you're getting more ionization on the ionosphere. But sometimes you can get too much of a good thing. This is just thing showing one of the sites that lists a bunch of these indices. You can see the A index and the K index and the X-ray. There's proton flux and electron flux and aurora activity. The magnetic one, which is the B sub Z. We'll talk about that one. And they do these like at least daily. I got one this morning. The solar flare index was the first one up here. So whenever this was, March 2023. I don't know what today's is.
It's around 110, I think.
Okay.
Which is good. Is that a serial number? SN?
A sunspot number of sunspots,
Oh,
and the other one's solar flare index.
Okay. What's the index scale? Like, what's the range you see?
Actually, I don't remember that one because it's not a question.
It's 0 to 250, isn't it?
Oh, that's the sunspot number, but the index may be similar.
Okay.
I don't know. Most of the indices tend to be like 1 to 9. I'm not sure what that, obviously that one's not 1 to 9.
Yeah.
It's 140. So how does a higher sunspot number affect HF propagation?
Say, hey,
I would go with that. Okay. There we go. 60 to 300.
I think something started.
I was wondering that, why don't we just shift the whole thing down from 0 to 240? Whatever.
I don't know. Why did they measure it at 10.7 centimeters?
Yeah. It's like,
It's just somebody decided that's a good place to measure it. Huh?
It's like that's measurement from where?
Wavelength,
Wavelength.
Oh, at the wavelength, okay.
whatever frequency that turns out.
It was like 10.7 centimeters wide or something.
That's fairly high. That's in
Maybe
the gigahertz.
if you calculate the frequency, maybe it's a nice even frequency.
Maybe. But I don't know. 10.7 into 300 isn't going to be even,
Okay,
is it?
I think it's kind of weird.
Well, all right. And it measures solar flux units, but I don't know what a solar flux unit actually is. And they're kind of all related with A index and the K index. Usually they increase together. The difference in the A and K is, and I always get them backwards. One is long-term, one is short-term stability, or one of them, which I think is the K, I'll probably be wrong, does it like every 3 hours, and the other one does it daily. We'll get a chart for that. So what is the solar flux index? Dog. Yeah. All you have to remember is the 10.7.
Weird number.
so know that weird number, nobody knows where it came from.
And I think everybody knows the 20 meter is the go-to band, night or day.
Yep.
Summer, winter. And the higher bands, 15 through 10, really don't work well if you have low solar activity. So they've been, I guess the 10 meter has really been great.
It's been good. Almost all
But we've
the
had
time.
a lot of solar
2
activity.
o'clock in the morning, I've seen 10 happy, which I thought was kind of amazing.
At what point in the solar cycle does the 20 meter, come on, move the Tinkerbell, support worldwide propagation during daylight hours? Delta. I would go with Delta.
About 20 meters failed during bad solar.
Well, everything fails if you got so a lot too many solar flares or coronal mass ejection.
Yeah.
Like I said, too much of a good thing can make it worse.
If there's very little sun.
Or if you get a geomagnetic storm.
Okay.
Which of the following are least reliable for long distance during low solar activity? It's the long one with 3 of them. Okay, the sun rotates on its axis every 28 days, although I've seen a lot of things that talk about the surface of the sun rotates at 28 days, not necessarily the center. I don't know, because it's kind of like a liquid. So the outside's turning, and so the sunspots that you see are rotating on that surface. So they vary over this 28-day cycle because obviously half the time you're not going to see those sunspots because they're on the other side. And that's why you get this cyclic effect from the sunspots. And it affects the lower frequencies, medium frequency and low HF bands. What causes HF propagation conditions to vary periodically in a 26 to 28-day cycle?
Or
Not the moon?
Full tonight, all everybody howling.
Okay, we can have what's called a SID, or a sudden ionic disturbance, which is due to solar flares and solar particle events, where it's actually ejecting material, form of plasma or something. And that can really affects the D region, which is the lowest region of the ionosphere. Actually, I think probably should move those things up where there's 3 layers. There's the D layer, the E layer, and the F layer. And the F layer in the daytime with a lot of solar activity splits into F1 and F2. At night, it collapses back to the F layer, which is lower altitude, and the D layer disappears. So you don't really have a D layer at night, and that's the one that absorbs all the low band HF during the daytime. If you get enough ionization on the D layer, it becomes an absorptive layer or attenuating layer. I'm not sure what happens, except the signal goes in, doesn't come out. So these disturbances can increase the D layer, which is going to make it more absorptive, and you're going to lose the lower bands in the daytime more than normal.
Do they actually absorb, or they just allow it to go through?
No, absorb. The higher frequencies are the ones that make it through.
So they won't pass.
No. In the D layer, I think it's trying to refract, but the losses are so great that it doesn't make it. But whether or not it refracts or goes straight through is a function of the critical angle, which we'll talk about later. It takes 8 minutes to travel from the sun to the earth for light, X-rays, any of the radiation. It takes a day or 2 or 3 or 4 for particles to get here, depending on, I guess, their velocity, because it's 150 million kilometers. So what effect does a sudden ionospheric disturbance have on the daytime ionospheric propagation? Bravo. Approximately how long does it take the increased ultraviolet and X-ray radiation from a solar flare to affect radio propagation on Earth? 8 minutes. Yes. Ultraviolet is ionizing radiation. So
It's not just the X-ray.
it's basically the lowest level of ionizing radiation. So, and that's the one when we talk about safety and exposure, that's basically the one that you're looking for, plus the radio waves, which generate heat, where ultraviolet and X-rays and all the gammas and all those things can modify your DNA, which I understand is not a good thing.
Yeah, it could only help me.
Okay. Corona holes. Every once in a while, a hole opens up in the surface of the sun, and it lets out a magnetic field. Exactly how that happens, I'm not sure, but that magnetic field escapes and can cause effects here on Earth with our magnetic field. And it also allows what they call the solar wind to escape. And then you have coronal mass ejections, where you're actually ejecting mass in the form of plasma, which is basically highly ionized material, where you've put in enough energy that you actually are ionizing, separating the electrons from the atoms themselves. So you've got the ionization there. Same thing. I think somebody asked about it a while back on spacecraft reentry. Why we lose communications is because of the plasma that's formed from the heat, and it's a great ionizing barrier. So there's no radio transmission in or out during that period. And it can take up to 15 hours for those particles to actually get here, or longer. And they definitely disturb radio communications depending on the amount. If it's a coronal mass ejection, so far, at least in modern history, they've all missed us, because it kind of shoots out of the sun in a certain direction, and the sun's rotating. So we're only in trouble if it's, ejected just before it's facing us and gets the right amount of time. It's my understanding that if we had a big one like the one that missed us here a while back, it would take out the power network.
Back in the 1800s when we got hit by one.
Yeah, but we didn't have the kind of
I know.
Power.
Worse nowadays.
Yeah. And the problem with the power network, my understanding is it takes about 2 years to build a new transformer. So if you take out a bunch of transformers, you're SOL.
Especially the big ones, it's.
And we don't seem to have a stockpile of spares.
No,
It costs $1 million each.
probably the state of.
It's going to cost a lot more than that.
2 years. According to that, so some organizations are stockpiling the ones that they are expecting to deploy a year or two from now.
Smart people.
Well, otherwise they can't get them.
Yeah.
And I'll bet the state of Florida probably has 3 standby portable transformers that they can move into place,
Cool.
because they're expensive as hell. I used to haul them for Montana Power.
I wonder whether, if they knew that one was gonna hit there, if shutting down the power grid and isolating stuff would help, if they would break the. Pull the disconnects and basically disconnect the lines from. the rest of
Yeah,
the
maybe.
grid.
It might protect the transformer,
Yeah, basically that's the concept.
because that's what you need to protect. It
Yeah,
wouldn't.
if they isolated and basically just said, sorry, world. We're gonna
Yeah,
turn
well,
power off for a day.
An hour later, it's going to go down.
We'll turn it off for a day
Yeah, I
or
mean,
so.
they know these things are coming out of the sun and they can predict when they're gonna.
Yeah.
Visually they'll see.
Visually, yeah.
Oh,
they
yeah,
see it high
yeah.
frequency
Yeah, they know when they're
radiation.
coming. And you got 15, 20-hour warning.
Yeah,
And not a lot of time.
but it's enough that the utilities could respond and just gradually shut everything down.
It's enough to hook up my generator.
Well, your generator's gonna get impacted too.
Well, no, the
You might want to wait, hook
Yeah.
up the
The
generator.
generators wouldn't be affected very much, the local ones, because you don't have that big antenna called power off.
Right.
Absorbent stuff.
Yeah. EMP is the other thing around.
Yeah.
Oh, yeah.
So how long How is long distance radio communication usually affected by the charged particles that reach Earth from solar coronal holes? Yeah, we should stick with VHF, UHF. Not affected.
At that time.
It doesn't depend on propagation either.
There has been some ducking.
Huh?
So there has been some ducking with 2 meters against a week or so.
Oh, yeah, there's a little bit, but basically it's point to point for most of the. How long does it take a coronal mass ejection to affect radio propagation on Earth?
Delta.
Okay. Now, we talked about the solar flux index a little bit, and there's what a solar flux unit is. 10 to the minus 22 watts meter square meter. No, square root of
Oh, that's.
Ten to the negative 42.
yeah.
Of the
Per hertz.
root of the frequency.
But
Gee,
that's nice form. You don't have to know that.
Is it one
Yeah.
over all that stuff?
Huh?
It's 1/10 to the 22 watts meter squared.
Per meter squared.
Yeah.
per hertz.
The K index is one of them that they track, which was on that first chart showing all of the ones with a nice picture of the sun. And that's the short term. They update it every 3 hours. And the A index, they do it daily. So that's basically the difference. One is a daily average, and one is every snapshot every 3 hours.
What positive and negative derivate or deviations, what does that mean for with respect to the K index? The deviation of what with regard to what?
Maybe they're averaging or just telling them the max the average.
This or something with the max and min is.
Well, when they do the K, they take a snapshot. So that's what the actual is. And then they're also providing what the maximum positive and negative values
Last
were.
3 hour interval.
Yeah.
Okay.
Yeah,
So current plus max and min over the last.
right.
Okay.
That's, I think. And obviously, those are measures of disturbances. So the lower the better for the A and the K. This chart just kind of shows the relationships where the A index is like 0 to 400 for really severe. The K index every 3 hours is giving you a 0 through 9 rating. So what does the K index measure?
It's a tough one.
Baker.
The red one.
Or did it skip ahead?
I really got to get a new mouse.
You should be able to
Your
use
mouse
the
tired?
left and right keys on your keyboard, I think will navigate to the
Yeah, probably.
least usually around.
Let's see.
Or page up there.
Possible.
Get rid of that.
There we go.
And then you don't have to go right click back and just hit the left right.
So what's the A index measure? You didn't see the last slide.
Charlie.
Long time.
Geomagnetic storms are disturbances of the magnetosphere. There's a thing later on where they talk about the interplanetary magnetic field, which I'm not exactly sure. I thought our magnetic field was pretty much confined to the Earth. And it didn't say inner, it said intermagnetic field. interplanetary. Oh, and down here it's just the planetary, but later on there's some, which was very confusing. Anyway, these geomagnetic storms are going to affect the outer ionosphere, the F2 layer, which is only there during the daytime. It can cause the auroras to increase, like we saw a while back when we had that big storm. And auroras were reported in Georgia and North Carolina. You could see them. Anybody do any aurora bouncing?
Not intentionally.
I understand it's not very reliable anyway.
Moves a lot.
The high latitude in whatever you call it in the southern hemisphere, is that still a high latitude or a negative high latitude?
Yes.
In other words, towards the poles are affected the most. I'm not exactly sure why, other than I guess the magnetic field is the strongest up there.
I think if the particles concentrate, they go in the Van Allen belt.
They don't
Concentrate.
dense.
As a result of the solar wind and the magnetic cloud, the K sub P index, which is, I guess, a variation of the K index, indicates part of that disturbance. There's a nice picture of a storm and how it affects the magnetic field and really distorts it. Of course, that's just an artist's conception. I don't know if that's how it really looks or not. What is a geomagnetic storm?
Oh. It's a thunderstorm. I think it would be more delta.
It's ripples in the force.
Yeah, that's a good one. Trying to figure out what fun you could have with that energy.
Yeah.
Time space continuums.
How can a geomagnetic storm affect HF propagation?
Delta again.
How can it benefit radio communications? Yeah, that's the only good one on there. Okay. Electromagnetic waves are composed of an electric field, the E field, and a magnetic field we call the H field, and they're orthogonal or at right angles to one another. We normally only care about the E field. Most everything we do with antennas and transmission is how it affects the E field or generates an E field. And I wish I could show it. I had a really nice little video that was done by DirecTV on how that works. But the way they explain it is the acceleration and deceleration of the E field or the current along the antenna. Since it's nonlinear, it's a sine wave motion, so you got acceleration and deceleration, causes that E field to separate from the antenna. It's pretty easy to see in the video, but the actual physics of how that happens is still kind of mysterious, but it's due to that acceleration deceleration that causes it, instead of a nice round shape, you get this kind of oblong thing and it separates, and then you get the next one. But it's copyrighted, so YouTube wouldn't let me keep it. But you still have the magnetic field along with it. And those are kind of oscillating at right angles, but as one increases, as the E field increases, the magnetic field decreases and vice versa. So how are component fields of an electromagnetic wave oriented?
Charlie.
They're not 90 degrees out of phase?
Okay, you can do that.
Well, they are, they,
Yeah,
they are.
there's a 90 degree.
Yeah, but that's not the right answer that they want.
Gotcha.
Although I think they're out of phase. In what direction does an electromagnetic wave travel?
The alternative.
Okay. Index of refraction. We normally have always thought about that with light, but that's an electromagnetic wave, and so is radio waves, so they behave the same way. So when you're traveling through some medium other than free space, it has a different density, and the wave travels at a slower velocity than it would if it was in free space. So it's going to be something less than the speed of light. And that difference is called the refractive index or index of refraction, which is that ratio between the speed of light and the velocity in the medium. So like in a copper wire, typically it's something like 0.95, 0.98, travels almost at the speed of light. In something like coax cable, because of the capacitance and stuff, it may be down as much as 0.6. Some of the really lossy stuff.
This says a index, as a ratio. The
Mm-hmm.
ratio is something to something, like
Right.
1, or, but you're saying it's 0.9. Is it
Well, it's going to be
0.91?
1 or less. Can't be greater than 1.
Okay, so is it,
Because Einstein said it couldn't exceed the speed of light, right?
is the ratio something to 1?
Right.
Okay,
So it's whatever the velocity is, not the speed, divided by the speed of light in free space, which is approximately 300 million meters per second. What determines the speed of electromagnetic waves through a medium? Okay. Moon bounce. Anybody done moon bounce?
Antenna costs too much.
Huh?
The antenna costs too much.
Yeah, I have a friend that does it or has done it, but he's got money,
Yeah, if you're gonna do it, you better have.
although as far as I know, he never contacted anybody, just the echo back. Then he said, you say, hello. Hello.
ooh,
You can talk to yourself and make a DX contact for it.
Yeah. When people actually do it for making contact, you kind of have to schedule it and you got to get somebody that's the same distance away and where you can both obviously see the moon so you can bounce it. Huh?
It's full moon tonight.
Oh, very good.
Well, the moon is
well,
always.
but that should not affect it though, because the moon's gonna be the same mass all the time. It doesn't,
Oh, it doesn't change shape?
it doesn't.
Oh,
What you-
damn.
What you see changes.
Oh. Okay.
And where you hit it changes too.
Yeah. So
Yeah,
you
that's
should-
the other problem. It's not a smooth surface.
It's not that reflective.
So it's not like you're gonna hit it and it's gonna bounce where you think it is. You hit a crater, no telling where it's going.
But it also depends on the beam width of your antenna.
True.
I mean, if you're shooting something that's 10 degrees up in the, 10-degree beam width up at the moon, you're
Right.
probably gonna cover the whole surface of the moon. The only part you're gonna get reflected back off is the sphere,
Yeah,
which is perpendicular to the or direction. The incident angle.
right.
So
But-
it's gonna scatter in all directions when it hits the moon. But the only part that's gonna come.
But
back-
remember, we're sending up a lobe, kind of
Right.
elliptical
The
shape,
correction of
so.
beam width of the lobe versus what's angular. Angular distance of the width of the moon.
How much of it actually gets reflected back.
Yeah,
Yeah, because it's gonna absorb some, because it's moon dust, which is probably not a good reflector. I wouldn't think.
Oh, no. So that water.
There's one of the typical, there's 16 Yagis there.
Oh. Haven't fit my day. It's just the rotor part, the azimuth
Yeah,
and rotation is like $1,500 or something.
yeah, to handle that weight, sure, yeah.
For God's sake.
I just wonder if I could do it with my 5 and 6 meter satellite dishes where I work. We've got a couple spare at this point.
Probably.
Try it.
How fast can you move?
The problem, yeah, the tracking I don't have, the C-band dish that we're Indy where I'm gonna be. So
There was a thing on YouTube I saw a while back, and this guy, some doctor type, claimed he hit it with a 100-watt radio.
antenna game.
You must have really good gene.
Well, it turns out you gotta do it at apparently a very low angle to the moon and some other stuff. And of course he had a, preamplifier on the antenna, things like that.
There's books written about this. It's
The brute force way is like that. Really
Yeah.
big antenna array and a really good receiver. So what's the approximate maximum separation distance measured along the surface of the Earth between two stations communicating by EME?
It's good old Delta again.
Okay, the average or mean moon distance is 248,000 miles. It's an elliptical orbit. So we have an apogee and perigee, where perigee is the closest point to the Earth, and apogee is the farthest distance to the Earth. So obviously, you want to try to do this when it's at perigee, because the path loss to the moon, my understanding, and I assume that's probably the best case, is 251 dB. So you got to make up for a lot. It's not like a couple dB loss in your feed line.
10 to the minus 16. 17.
When scheduling EME contacts, which of these conditions will generally result in the least path loss? Okay, you can have what's called libration fading. It isn't because the moon is fluttering, but because of the irregular surface. You don't know where the maximum strength of the signal is going to be, even though it's very broadband, broad width. It still varies because of the mountains and the craters and the fact that it's moving. So what characterizes libration fading of an EME signal? Meteor scatter. Anybody done meteor scatter? As a meteor penetrates the atmosphere, it's basically causing a little plasma, so it's ionizing a trail. through the atmosphere, and it leaves this little circular trail behind it that lasts for maybe a few minutes. And I guess its biggest effect is in the E layer. So you can bounce some of the higher frequency signals off of that meteor trail, that ionized little tunnel or tube in the 10 meter to 2 meter range up in the higher frequencies.
Makes me wonder if you could work stations when the Dragon capsule comes back and lands back on Earth.
Yes.
Got a very nice big trail there for a good
Yeah.
while. You can see it across the sky.
Yeah.
I got to see it once
Actually,
landing in the Gulf.
you can do it off of aircraft. They leave an ion trail. Even our stealth, because that's one way you can track them, is the ion trail. They haven't figured out how to, as far as I know, they haven't figured out how to do anything about that. That's kind of,
Drag some grounding wire down.
Get your ion detector out.
I should say jet aircraft, not propellers.
Yeah.
They don't, I don't think they can ionize the atmosphere, but jet exhaust does. On meteor scatter, you can get this forward and back reflection effect, so it affects the hop distance basically. And it's my understanding these things only last up to maybe a minute or two, or best case. Usually it's like 30 seconds or something, because most of the meteors aren't that big, so they don't leave that much of a trail.
What am I missing on that diagram? What's the difference between those two? Other than the angular distance, 2 theta. Don't see any difference. Except for that well. They're calling one forward and one back. Just don't get it. Just a big-
I don't know, unless their arrows are wrong.
Well, the TX or transfer.
I would think that,
Well, isn't the, like the one on the right, forward reflection, yeah, so that's going to the right, isn't the other one going backwards?
No,
Arrow has
an
an
arrow.
but I think on forward reflection, the transmit and receiver should be swapped.
Yes.
Yeah.
that would make more sense.
I didn't screw up the chart.
I didn't say you were wrong. I just
No.
couldn't figure it out myself.
Yeah.
It's hard to find a lot of these things that really are correct or fit.
So what's supposed to be showing us though? If you're pointing,
If you're
more
doing forward
acute.
reflection because you're taking advantage of the fact that the meteor is traveling, okay, you get a longer hop than if you're doing it, you're bucking it versus boosting.
Again, what an elaborate setup that would have to be to track it and.
It's just a conversation chart.
yes,
Yeah.
When a meteor strikes the atmosphere, a linear ionized region is formed at what region of the ionosphere?
alpha.
That's about the only thing the E layer is good for, that and scatter. And the D layer just sucks up stuff. That's not any good.
We ought to get rid of it.
Well, you do at night.
Okay.
Start position, maybe we'll get rid of it.
Which of the following frequency ranges is most suited for meteor scatter communications?
Charles.
Okay, tropospheric scatter weather conditions don't normally affect HF propagation. It starts affecting microwave propagation, VHF, UHF, and above. It has a little effect at VHF and UHF. But primarily in the microwave range. I don't know. It's probably too short a distance to a tower to notice it, but it should really have an effect on cellular. Probably doesn't work as good in a rainstorm outside, but I don't have any evidence, but theoretically it should affect it. You can have a temperature inversion where you wind up with a cold area temperature wise above a warmer one in the atmosphere and
That's
get
the opposite.
you're right, the opposite. An inversion from normal.
Invert that.
It forms a duct. Okay, and because of that temperature difference at those boundary layers, the signal can reflect or refract off of it. So it actually looks like a tunnel. So you can kind of tunnel through that duct. They tend to form over water more than any place else because it usually requires a lot of moisture in order to get that effect in the atmosphere. And you can go like 100, 300 miles, somewhere in that range. If you're lucky enough to get one. Of course, I'm not sure how you would know.
You would be making communications further away than you normally would be.
Yeah, I guess. Well, 300 miles is a lot better than line of sight.
You get that in broadcast band. I was in Virginia back in college, working in a college station, and we were listening to a Houston, Texas station. Coming in conducting for half an hour, crystal clear.
Wow.
We've got that at our work too. We've got a chart that they keep up in the control room, which shows where the current ducting is, because we've got listeners that call in. I can't hear your radio station, it's something else. Yeah, we can't do a thing about it either. It's the ducts right now.
Okay, so you can predict tropospheric propagation by looking at some of these prediction sites. The one that you need to know a little bit about is the Hepburn site. Are you familiar with Hepburn?
I don't.
Okay. I guess it's still active because the question is still cool. And he shows, I think I have a picture one, kind of a graphical representation of the propagation and where ducting can be. In fact, there's one, of course, it's an old one from 2023. And I don't know. You have to have more data that's on the site to tell you what the different colors and things mean. And it may not be any duct in that particular thing anyway. I don't know. But that's just what a typical Hepburn map looks like. And they update it pretty frequently.
One we have has more ellipsoids kind of showing the general regions where if you have a station somewhere in here, it's probably going to get, or there is hearable somewhere else on the other end of that. So you'll have different shapes along the edges of the coast and so forth.
Okay.
Quite like the heat maps.
Atmospheric ducts capable of propagating microwave signals often form over what geographic feature?
Check.
I thought it was mountain ranges. What's a typical range for tropospheric propagation of microwave signals? Aurora propagation. This is another one of the E-layer means of propagation, which means it's kind of unreliable and sporadic.
It's daytime,
It's what?
would it be daytime?
No, the auroras, they're 24/7 somewhere.
Just see it at night.
Or it's-
But
talks
you
about-
see it at night, but it's still there.
Right, but it says it's interaction with the E layer and.
Yeah, but the E layers, there 24/7. The D layer goes away.
Oh.
The E layer is still there.
So the F zone.
F shrinks at night and D disappears.
Okay.
E's always there. And CW is the best mode. Although I would assume that some of the digital, like FT8, would be good too.
I think so.
Used in frequency meaning just spread out.
Modulated, so I guess you're going to get some additional frequency modulation.
But it's.
Why, I'm not
Moving.
sure. It's right.
Yeah.
It's very dynamic.
Talking about like with the phase distortion.
Yeah. Doppler shift.
Yeah.
Interference. From the-
And phase change is basically the same as frequency
Right,
change.
right.
What's most likely to result in auroral propagation?
Big.
Yeah, magnetic storms. Which of these emission modes is best for auroral propagation?
Charlie, let's get one of these. Yeah, see that. Yeah, too.
Let's see. Okay. Some of the bands, like the higher bands, work pretty good in the afternoon, but they kind of get worse at night, where the lower bands pick up at night because they're no longer being absorbed in the D layer. So they can make it up through the E to the F layer.
Is 20 meters a little bit of an exception, meaning that it's
20 meters is one of those that's, it doesn't, it's basically the same day or night, summer, winter.
It's closer to L.
I mean, I've worked 20, as the sun's setting and it gets dark. And like helping out field there or something, just make contacts, the band's all noisy, noise floor is way up, and as you get into the dark, as the sun goes west of us. Whole noise floor and the signal propagation seems to kind of drop out,
Yeah,
but earlier we were seeing 20 supposed to be good day and night.
right.
But I've seen a change.
And I've, like on FT8, I've seen more activity on like 17 and 15 at around midnight.
Yep.
Like, see Japan popping up all over the place,
Yeah.
which is counter to what this says.
Yeah.
Although, I guess you got to take into account it's probably early morning
Yeah.
in Japan.
Yeah, right.
Yeah.
And likewise, late for us is early as midday or morning for Europe and so forth. So,
I have that hand clock thing and you can see where the daylight and dark is.
yeah.
The gray line.
And as Japan and them wake up, the signals start. You can watch it. It's amazing.
What should be done to continue at a long distance contact when the muff for that path decreases due to darkness? course, we haven't talked about muff yet.
Bikini,
Well, it's ballistic.
or 40.
Ballistic.
Polarization. We talked about that before, where vertically polarized means that the E field or electric field is moving vertically with respect to the surface of the earth. When horizontal is it's moving parallel with respect to the surface of the earth. If it's circularly polarized or elliptically polarized, it means it's rotating with respect to the surface of the earth. If it's the same signal strength, amplitude, as it rotates, it's circular. If it varies, or you get a higher signal in one orientation than another, then it's elliptical, which is the general case. So when you refract off the ionosphere, it magically turns it into an elliptical polarization, even though it's linear going up. How that works, I don't know. But it says in the book that's how it is. So, what are circularly polarized electromagnetic waves?
Waves that circle the earth.
Oh, that's a good one.
I believe it.
Okay, so we talked about sunspots where higher numbers are better. The solar flux index, where they measure it at 10.7 centimeter wavelength. 20 meters isn't really affected by the solar cycle. Although I guess I take exception to that. I think it's affected. It's just
I think it's
whether it's
less.
high or low in the cycle, it's going to be the best band,
It's less effective.
but you're going to have less propagation on 20 at the minimum of the solar cycle, I think. There's still going to be
It's gonna be
relative,
It's gonna be better than the other.
right? The higher bands aren't as reliable at low solar activity, requires more ionization. Sun takes 28 days to rotate the surface. So those sunspots come around every 28 days. I'm not sure how long they last on the surface. Could be like that spot on Jupiter that's been there forever.
Storm.
X-rays and other rays like that take 8 minutes, and particles take 20 to 40 hours to get here.
Doesn't, oh. go
What?
ahead. Go ahead.
No, what was the question?
Well, the sun rotates, does a one rotation every 28 days.
Something like that.
Isn't that real close to what the moon does around the earth?
27.
Is that just coincidence?
27 diffraction days.
Some.
Somebody set it up that way.
Yeah.
Oh,
Yeah.
Here's on that column and
just happened to notice that.
Oh,
You may know
I think it's coincidental because, no, I don't know. We do know that the moon does rotate around the earth, but the moon doesn't rotate relative to us.
It rotates it.
yeah.
It revolves at the same
Right.
rate that the earth does.
Right, but the same side is always facing us. So it's rotating, but
So.
it does one rotation per Earth rotation. Okay, geomagnetic storms are disturbances of the Earth's magnetic field. high latitude is affected. VHF signals can be bounced or refracted off of auroras. We talked about E and H fields at right angles. The index of refraction is the ratio of the speed of the wave with respect to the speed of light. Moon bounce, you can do 12,000-mile contacts. Perigee is the closest portion of the orbit to Earth, where apogee is the farthest or most distant. And libration fading is what they call the irregular signal that you're getting from bouncing off of the moon's surface. We can get meteor scatter in the E layer, in the higher HF bands. You can get tropospheric ducting due to temperature inversions formed over water. And they can go up to 300 miles for microwave. Apparently, they also can have them at broadcast, MF, right? CW is the best mode for auroral propagation. The low HF bands work better at night because there's no D layer. And circular polarization is just a rotating electric field. Or I should say a waveform with a rotating electric field.